questions. Now, again, this is about 2 weeks of the general course, which has been condensed, and I've added a few things. It is quite important, so a lot of it is the general course, which we are going to just go through very, very quickly. But there are a few tricky questions towards the end where you have to really interpret what's happening in scenarios. So, first page, position time graphs. If we chuck an object's position as it changes over time, we are going to be able to determine a few things. For example, I've now got an object starting 2 meters away from something, and in a time of 10 seconds, it moves to a position of 6 meters away from some reference point. It's moved 4 meters in 10 seconds. If we were to determine the gradient, could we write this down, please? So really, we are dealing with a rate of change of distance with respect to time. That is what the gradient for this graph is. We're going to call that speed or velocity. Okay? Now, in maths, normally your axes are dimensionless. So you would just have x and y, and you would just go y2 take y1, x2 take x1. But now, in this context, it's now the change in position, S final minus S initial, divided by the change in time, T final minus T initial. Now we've got units, meters, seconds. So now, gentlemen, every gradient in physics has units. You need to work out what they are. Okay? Now, for this, the units are quite simple. When we get up to Newton's laws, and you've got force and acceleration, and we can use dimensional analysis to figure out what the gradient manifests itself to be. So, please remember that. All right, every single gradient from this point on in physics, years 10, 11, and 12, you need to include units. If you don't, you're going to lose marks. Okay? So, let's just throw down. Let's start off in maths mode. So we'll go, what was maths mode, red or blue? I think red. We'll go m equals x2, no, it's not, it's y2. Now let's chuck it into the context of S2 take S1 over T2 take T1 equals delta S over delta T So simply put, the gradient gives us the speed of an object. Now, funny thing, they changed in the data sheet. There used to be a delta in the year 12 data sheet, which is what every student gets and they can take into every single test and exam. And they removed the delta. And the equation pretty much went, it used to be, this is just a quick little side story, A equaled V take U over delta T. Delta stands for the change in time from time 1 to time 2. And we can calculate it by T2 take T1. But they went, oh, the delta, that's too tricky. Students won't understand. And now the equation is simply that, V take U over T. Now, I'm hoping that you guys don't mind. I'm going to include the deltas in my equations. And it simply means the change, the rate of change of position with respect to the rate of change of time. Okay? Not only, I'm just going to write here, we can get some semblance of direction, because remember, we haven't committed this, we haven't written this down yet. Speed is a scalar, velocity is a vector. So let's just add.
So what was the difference between scalar and...
Vector has direction. Okay. All right. So if I said that the object's traveling 5 meters per second, that's its speed. That's speed, scalar. But if I said that a car is traveling 5 meters per second north, that's velocity. All right. So now we can add direction. We can get direction off a graph. Now again, last trimester I would have forced you all to scribble this down, but it's a waste of time. Here's a graph. Let's have a look at it. It's saying that in 10 seconds, a car went from 0 to 50 metres, and then it was stationary for 50 metres, and in fact it was stationary for 35 seconds. And then in the last 5 seconds, it went from 50 back to 0 metres. Okay? This could almost be you jogging to one side of the oval, staying there, and then sprinting back. So let's have a look. Rise over run. Now let's go plus 50 over 10 equals plus 5 metres per second. The next one obviously is 0 over 35, which is 0 metres per second. And then here, this is where some students... Oh, hang on. Did I? That's just
30 or 35? Or
30. Sorry. I don't know why. This part here, this is where some students make errors, that the rise, S2 take S1, is 0 take 50, is negative 50. The rise is negative 50 because it's going downwards. So that's where we go negative 50 over 15 seconds. And 50 over 7 is 7, 1 recurring, or 7, 1 remaining. It's negative 7.14 metres per second. Now, again, it's kind of giving us direction because now we've got an outwards journey is in the positive and a return journey is in the negative. So really, we're getting a tiny bit more information by the positives and the negatives.
It's not happening. Minus 7. So
Yeah,
it's minus 3 return.
Oh, yes, I had a different graph. Thank you. What is it? 15 over 50 over...
It's like 10 on 3.
All right, cool. 3.33. All right, sorry. Now we're back on track. And I'll highlight again that the value of the gradient can indicate to us some semblance of direction. Before we go on, we've got some questions where you could, and you will encounter them. What if I wrote up here, east? Then all of a sudden, this is no longer a position time graph, this is a displacement time graph. And then we could say that everything in the positive is east, and if we went into negative territory, where are we going? West. All right? Now we could say, all right, positive. So all of a sudden, boom, I've gone from a speed to now I can say that the outwards journey was 5 metres per second east, and then the return journey, travelling in the negative direction, that's west. Okay? So you will see some graphs further on in this booklet have actually got direction in their units as well. They're changing it from a position time to a displacement time. And remember, anytime you are given displacement, it basically follows through. I could have written here 50 metres east gives 50 metres east. Negative 50 east, well, that's the same as writing 50 west. And we could then go 50 west divided by 15 is 3.3 metres per second west. Right, so just keep that in mind. Turn over the page. No, don't turn over the page. Look at this graph still. I took probably 3 measurements, 1, 2, 3. We could have had this out on the oval with 3 stopwatches. We put a kid at 50 metres with a stopwatch. Ready, set, go. And a kid starts running towards him. When he gets to him, he's stationary. Kid's watching, writes down the time, 10 seconds. And then Mr. Murray goes, ready, set, go. And he runs back. And the kid, 30 seconds. And then he watches him, and then he gets back to Mr. Murray, 45 seconds. You took 3 measurements of time, and they were all spaced out. 10, 20, 15. All right? Now, here's the thing. If I just had that, all I could say is I know where this person is. Bear with me. I know where this person is there, and there, and there. That's all I really know. So all I can get is his average speed. For all we know, when the kid did his outwards journey, he could have done this. Oh, try again. He could have done this. You know? But we only took one measurement at a time. And then he could have sort of wobbled backwards and forwards and, you know, done some lunges. Right? Then he could have sprinted there and then crawled the last 5 seconds. Okay? But we didn't have any measurements. We only had 3. And so all we can assume is that between 0 and 10, his average rate of change was 5 every second. And his average rate was 0 every second. And then his average rate, well, let's just go back to that. His average rate in the last one was 3.33 in the negative. What we could do is get more people, and we could put them every metre. Right? Every metre along, we could have a kid with a stopwatch. And as this kid runs past, everyone go, ready, set, go, look. And as the kid runs past you, you stop your stopwatch. Now, what might this look like on the graph? Every metre, we get a dot.
Then you could assume that he goes between 2 of them, he could also go somewhere else.
And then every metre, you get these dots. Well, now I'm going in time. Let's just ignore that one. And then he comes back, and so the kids with their stopwatches, they start recording again, and they're getting these. But then, all we can say, it's not. We could then say, all right, his average speed per metre. We could zoom in, and every dot would have its own. Oh, geez, no. Every dot would have its own little rise over run, rise over run, rise over run, rise over run, dunk, 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 dunk. All right? We're starting to get to the idea of instantaneous speed and instantaneous velocity. So, imagine now, here we have a graph with 3 runners, and they were instructed to run a distance of 80 metres. Okay? And we actually did this. Tristan, Ben and Kyle were from Trinity. I got their data when I was teaching at Trinity. And we didn't have a stopwatch every 5 centimetres. Imagine you just had an infinite line of stopwatches. And every time you ran past that stopwatch, it stopped. We would be getting so close to the instantaneous velocity. All right? What Excel can do, I actually had them every 10 metres. So this plot would have had 8 dots. 9 dots if you include the origin. And it's got this function in Excel where you can essentially smoothen the curves. It sort of gives you a nice smooth, where if there's any changes, it doesn't do a jerky straight line, it smoothens them. So it kind of cheats. It's not really an instantaneous velocity, but we can treat it, or instantaneous speed, we can treat it as instantaneous. What we need to do, however, is to draw a tangent to the curve. Have you learned how to do tangent lines to curves? Sort of. All right, turn the page. Instant velocity is the velocity at any instant. What we're going to write here above is tangent. The tangent at any instant. As I said, in our experiments, we are limited by how much measurements we take. We can only really, we've only got 20 kids. We use 10 kids on the course. We get a few kids to run, and then 6 or 7 kids stand around doing nothing for 20 minutes. To overcome this, it is an estimate, all right? So it does have its limitations. Here's what I would like you to do. In this little area here, I would like you to take your wrist and pronate it. I just want you to go and make a curve by flicking your wrist. I just want you to go like this. Ready? Like that. Just draw any curve. Rotate your wrist along.
Left-handed. Got it.
Get out. All right? Now, here's what we are going to do. On your curve, I would like you to pick a point. Okay? Any point on that curve. Now you get your ruler out. And what I'm going to do this on the screen for you. You're going to get your ruler so that it just kisses the point. I think it's called cusp. It's just the cusp. Now here's the thing. You've got to draw your line such that it just kisses the curve and then disappears. You do not want it to intersect the curve, because if it intersects, then it's not parallel at that point. A parallel point will just meet it and then travel off. So it takes a little bit of tweaking. You know, if I did it like that, look, it's going to intersect. If I had it too steep, look, it's intersecting. You've got to get just the right point that it meets at that point and then travels off. Okay? So I can cheat because I've got the graphics tablet, but I'm going to try to do it in one hit.
What?
No, see, I'm going to take him. I'm going to rotate him slightly. Okay? That would be my tangent. Yes, because I said his, didn't I? Yes.
He created it, so.
And from that tangent, if we draw the line long enough, it's going to cross a few grid lines, and then we can determine its rise and its run. So what we're doing is we're making a line that's parallel with the curve at that point, and the gradient of the line will equal the gradient at that point. But nowhere else on that curve will it have the same gradient. At the only point on that curve, the blue line is parallel with the black line at that point.
So is every point tangent unique?
To a curve, yes. If it's a quadratic, it's never going to be this. If it's a cubic, then there'll be a couple of points there and there, and there, and you know, there's a cubic will have points where the gradients there might be 2 points on that curve where it has a gradient of 3.2. There might be 2 points on that curve where it's got a gradient of 0, the turning points. Have you guys done cubics and like that?
Not cubics.
Not cubics. All right. Well, a quadratic, really, the gradient is always changing, and there will only ever be 1 point on the curve that has a gradient of negative 1.2. There it is. There might be only 1 point where it has a gradient of plus 2. There it is there. And it's continually changing. So it's a very unique shape. Let's get back to this activity. We want to find the tangent line to Ben, his curve, at the 14-second mark. So let's go back and identify Ben's curve at 14. There he is there.
So if here when it's it's not even a perfect curve, is it all right if it intersects the?
Well, you don't want it to intersect. That's the key thing.
I don't see how you could. Oh wait, actually.
So obviously, ignoring all other parts of the curve, you need to focus in, and I want you to try and draw your line so that it intersects and then travels off with,
Oh, so.
Okay. So again, that's not too bad. Now, again, what you need to do is to draw your line long enough so that you can then get the information off the grid. All right. Now, each grid line will have its own interval. So I might go from. I don't know where I'm going to go. Let's go along this line to that line. So what I've done there, gentlemen, is I've picked my horizontal lines, 1, 2, 3 lines. And if I zoom out, looking at the scale, I can see that each line is 5 meters. So mine, I've just picked that's 15 meters. Each line on my horizontal is 1 second. So here we have to estimate 1, 2, 3. That might be a half. I might estimate 3.7. And that is it. It's an estimate. So depending on your tangent line and your estimate of rise over run.
It's quite hard to see the graphs, the graph lines.
Oh, sorry. Yeah, when I printed it onto the paper, it's come out quite faint. I got 4.05. So hopefully
I'm really struggling to find what I got.
So gentlemen, again, it is an estimate. As soon as what you're doing is you're estimating the x values, you're estimating the y values, and really you're estimating the tangent line. There would be an appropriate range. If this was a test question, you might go accept anywhere between 3.7 and 4.3 or something like that. Right? So, but here's the thing: if you drew your tangent line far too steep and you wrote 4.6, I'm not going to, I'm not going to allow it because that was not an accurate estimate.
Oh god,
Okay.
I'm really
What
struggling.
did you get then?
I got 60 out of 5.5.
What is it evaluated numerically, please?
I don't know.
Oh.
30 out of 5.5.
What is it?
Which is just over 5.
Give. That's probably too steep. I
Hold on a sec, that was my fault.
I think you might have drawn it to, or have I stuffed up somewhere? 1, 2, 3,
No, you wouldn't have stuffed up.
3.5 plus 0.2. I imagine it's
Probably me.
probably you. Because have a think. For every 0.1 second, this is going to go up or down by 1.5. 0.15. 3 divided by 0.1.
They might have drawn a tangent for a different point from your own line. Maybe the tangent is a different angle because it's on a different point in your own line.
I'm pretty sure.
Yeah,
it's
the
on
tangent
10
doesn't really look that straight on.
What? Yes, it does. Oh, you reckon?
It should be a bit steeper.
You think it should be a bit steeper?
His tangent works.
You think it could be something like that?
No.
Yeah, I think that
No, that just doesn't work.
Again, that's why it's subjective. So we allow, due to this subjective nature of estimating lines, we allow a range. All right, the next one. Come on, gents, you can continue on with the next one. It says, find Tristan 20 seconds. Tristan is blue, 20 seconds. There he is. Wait, I missed it. Where is it? There he
Yeah,
is.
it's just under 5.
Tristan's endurance is pretty lackluster.
Boys, come on. There are a number of students that are going to be watching this video to copy down the notes. Let's get through this promptly. So, line up your ruler as best you can. Try and match. Okay. And then pick an appropriate line. Again, for me, there doesn't really seem to be any appropriate line. Again, I've picked 15 meters as my rise, and then I've got 1, 2. This could almost be 3 seconds.
Wait, so it's rise over 1.
Yep. So for this one, they're so close. I've got the black line is slightly steeper than the blue. Okay. So again, we've kind of picked 2 points that those curves are almost parallel, but I would argue that at 20 seconds, the blue curve is slightly steeper, meaning he was traveling slightly faster at that point. The last question.
I got 4.94.
Find the steepest point. Gentlemen, where on this graph do you think is the steepest point?
The end of Kyle's.
Yep, I reckon Kyle at 10 seconds.
I was quite quick.
So, last activity. Kyle at 10 seconds. And in fact, over those 5 meters, his gradient almost seems pretty constant.
Yeah, I almost got parallel.
Okay. there's a nice intersection. One, two, three, four. I would say 20 meters in about 1.3 seconds. And I think we get a bit of an issue with this. Yeah, 15.4. Gentlemen, that's a bit alarming because Usain Bolt in his prime could only really run about 11 meters per second. So there must have been an issue here. And I think the issue was with the person timing at the 80 meters and possibly the person at the 70 meters. There might have been an error because this gradient would have come from 2 points. It would have come from this person's estimate of time and that person's estimate of time. And what I think they have done, either the 80 meter has underestimated his 80 meter time and the 70 meter person has overestimated, and that 10 meter time interval is far too short, okay, to be travelling that fast. I think there is an error there. All right? No.
Yeah, maybe they were just like standing really close.
Or there's that, yeah, but you're right. Or they weren't standing at 80 and 70. Maybe they took a step towards each other. So instead of it being a 10 meter interval, it was wait, I've made a mistake. I've made a mistake.
Well, I've still got 15.5.
It's 10. No, it's not, it's 20. I was right.
Yeah.
I didn't make a mistake. So I think the error might have been in the recordings there. Okay? All right. Can we please continue on? Now, gentlemen, just from that, 2 key points. Position time graph, the gradient gives us the change in position over change in time. We call that speed or velocity. And if we have a curve, we've learned that we can draw tangent lines to estimate the tangent at a point on a curve. Okay? However, velocity time graphs is where it's at. We can get more info from a VT graph than an ST graph, so a velocity time. Let us please consider the graphs below. This could be a person travelling at a constant 2 meters per second. If I wrote on, it doesn't matter which rise over run we use, 8 over 4 is 2 over 1. The gradient there is 2 meters per second. Okay? And it's a constant. So for every second, that person travelled 2 meters. And we can see that they've produced a nice straight line, which has a constant gradient, hence a constant speed or velocity. If we take the gradient, take the gradient and plot it on its own graph. Then we get, I'm just going to join up this arrow, we get a VT graph because the gradient was the velocity. And now have a look. Now we've got the gradient of the graph is put onto its own graph below, and we can see a constant speed of 2 meters per second. Okay? Now there is an equation that we've skipped a little bit. There's an equation that says displacement is velocity times time. Now let me just hold off on this question. If this gentleman maintained that speed for 5 seconds, how far would he have travelled? 10 meters. 10 meters. Now, if I took this equation and said 2 meters per second multiplied by 5 seconds That's essentially the equation there. If I gave this to you as an algebraic question, well, that's pretty much where I'm getting at. Please keep it down. I'm just going to write, there we go. If I said, here's an algebra question, and we gave you this question in maths, Mahoney, we gave you this question in maths and you had no idea what those variables meant. They were just different bases, different algebraic values. You'd use your rules and you'd say, all right, rule number one, we evaluate the numerals first. 2 times 5 is 10. Then we go, all right, using our index laws, we get a per second cancelling with a second, s to the 0. And then we get m left on its own, and so the answer simplifies to 10m. Well, hey, that's the unit for distance or displacement. Okay? From a graph, what we can do is simply multiply v, which is the side length, by t, which is the side length, and the area under gives us the displacement. Okay? So this is an important, where am I going to write it? We can still get displacement. It's the area under the curve. We will summarize this later on down the track. In fact, I wrote it. Yes, Tristan?
Wouldn't it only be displaced if they're walking in a straight line?
It's only if they're walking in a one-dimensional plane. So they can only be walking north-south, east-west, up-down, left-right. You're right. As soon as they go north then west, they're no longer... You would have to make a three-dimensional graph.
They could be walking
And-
northwest, right? They could just be walking northwest.
As long as they were aligned on a northwest curve, then they could be travelling northwest or southeast. As long as... Hold on. Can we write this down, please? I want you to commit this to memory. The area under a VT graph gives us displacement. Now, I'm going to say displacement now rather than distance, because the next page should make it a little bit clearer. Okay? Yes?
Say on this, if you graph gravity, the acceleration to gravity.
Yep.
That would be a straight line going upwards.
Gravity is negative, so it would have a negative gradient.
Sorry, downward slope.
We'll get to that probably next lesson. All right? You're a couple of lessons ahead. All right. We can also get the next thing. The gradient tells us how velocity changes. Velocity is delta V over delta T. So that is the rate of change of velocity. So what we're going to write in our little box here is m equals y2 take y1 over x2 take x1. Now we're going to put it into physics content. Delta V over delta T. Well, in fact, I'm going to just shift him out. We could write V final minus V initial over T final minus T initial. Acceleration. So my laptop is struggling a little bit. Whenever my handwriting goes messy, it's because the laptop is struggling because it's screen capturing at the same time. So gents, I told you that we can get more info from a VT graph, Mr. Lind. We can get the displacement, it's the area under. We can take the gradient of the curve and that'll give us how the velocity is changing, and that's acceleration. Okay? Let's consider the following. A car starting at rest and taking 4 seconds to get to that speed. So let's write velocity, time. And we're going to put in 2 points at the start, 0, and at the end. Put a dot anywhere. It's just going to be a very simple sketch. Again, the car, for all we know, the car could be doing this. but we're going to be getting its average acceleration. If we've only got 2 points, then we're going to assume that the average rate of change looks like so. Okay. So, from this basic sketch, we can find out everything about it. It was, all right, it was stationary at the start, and in 4 seconds it accelerated from rest to 20. The displacement is area under. Now we're going to go a half base times height. We'll just leave it in geometrical terms for now. I'll show you, we can get some cool equations from geometry in a moment. But let's just go a half of 4 by 20 gives 40 meters. So while the car was accelerating, this could just be a car taking off from a set of lights, and in 4 seconds it gets up to, it's about 72 kilometers per hour. Well, it's 20 meters per second. It traveled 40 meters while it was doing that. The next thing, gradient, gives us the acceleration. So we could say A equals take 0 over 4. So every second it was increasing its velocity. Now, yes, let's just, you're absolutely right, but let's just write it as that for now. It's 5 meters per second per second. Every second it went up by 5. Every second up by 5. Every second up by 5. Every second up by 5. There you go. You got 4 1-second steps increasing with an average height of 5 every second. Okay? Now we're not going to write the units like that. We could, in fact, we could write it like that. We could write it like that. We could write, there are so many different ways we could write it. The most simplest way of writing it is ms to the negative 2. So we will write 5 meters per second squared. So this is known as a second order rate of change. A first order rate of change is known as velocity, and then a second order is the rate of change of velocity. The rate of change of the first order with respect is a second order change, and we call that acceleration. Okay?
Third order change.
Third order is called a jerk. A fourth order is called a jounce, but we don't go that far. Jerks are not useful to us, but have a think. It's not a joke, it's a jerk. Don't write this. Don't write this. Hold on. Hold on. Shh. Hold on. Gentlemen, have a think of a car. A car does not accelerate like that. It goes through gears, right? It goes through first gear where its acceleration is the most at a certain point and then it peaks away. It would actually accelerate like this as the gears change and as it reaches its top speed, okay? And so if I said, where's the maximum gradient here? Your acceleration is not going to look like this. First gear, second gear, third gear, fourth gear. It's actually, you're going to get, and I have to start thinking now how an acceleration, you're going to get something like this. First gear maximum, second gear maximum, third, fourth, and then eventually it plateaus out to 0. We don't care about third orders. Okay? The only people that do is NASA and JPL when they need to figure out the thrust of a rocket and how the force can affect the rocket. They even go for sometimes, apparently they went to fourth order in their calculations to make sure that any vibrations in the thrust of the rocket or the variations in the thrust did not affect the mechanics of the rocket. You don't want your rocket exploding. Now, have a look at this one. Jounce. That would be ms to the negative 4. Have a look. Have we got 4 minutes left? Something like that. Let's get this last one completed. Gentlemen, I've got this kind of curve. Now, this is a position time graph. So have a look. This is a person traveling away. I haven't given you their position on the y-axis. We're going to estimate it. But have a look. They're getting faster. This could be a person over 6 seconds. They start off walking, and then they're jogging, and then they're sprinting, right? And then we don't care about what happens if they smack into the wall flat line. We don't care after 6 seconds. But let's just imagine that we took a gradient. Now I'm going to add one more gradient to this. Could we just add the last gradient here, that at the start they were stationary? Alright. So again, they started at 0 stationary. After 1 second they were walking. After 4 seconds they were jogging. And then after 6 seconds, well, call it 6, they were they were jerking. It's not as funny now, is it? No, it's inappropriate. All right, let's plot these points. What we're going to do, we're going to take the gradient, which we, again, pretend that we had some students that measured rise over run at those 4 points. Now, let's try and superimpose the values down here. We're going to go 1, 2, 3, 4, 5, and 6, equally spaced. And then we're going to go, our velocity needs to go up to 5, so we're going to go 1, 2, 3, 4, 5, and 6 for fun. Again, we only have 4 bits of data, so we have to be, we're estimating the average. We said at the start they were there. And then after 1 second, they got up to a gradient of 2. And then at the 4-second mark, they had a gradient of 3. And then at the 6-second mark, they had a gradient of 5. Okay? Ooh. Again, that's all the data we had. If we plotted the gradients every 1/10 of a second, we would have these bullets of dots, and then we would be able to figure out with more certainty. But we're just going to be estimating. In the last 2 minutes, gentlemen, we're going to create a bit of a complex shape. Okay? Look, we've got a triangle, we've got a trapezium, and we've got a trapezium. We'll call this area 1, area 2, 57. Area 51. In the last 2 minutes, could I just get you gentlemen to contemplate how you might determine the area of these shapes?
Mathematics.
That's it. L1 plus L2 over 2 times H. Or no, in this case, H1 plus H2 over 2. So we could determine, we're not being asked, but we could figure out the acceleration. So we could find the gradients at each. His gradient in the 1st second, his gradient in the 3rd, his gradient at 5 seconds. It's linear, it's nice and easy. But let's just go A1, half base times height. A2 is going to be H1 plus H2 over 2 times the length. A3 is going to be the same. And can we do all of this in our heads? A half of 1 times 2, that's 1 meter. 2 plus 3 over 2, that's 2.5 times 3, which is 7.5. Wait, 2.5.
Yeah, I looked at it before.
7.5 meters. And then the last one is 3 plus 5 is 8. 8 on 2 is 4. 4 by 2 is 8. So again, yeah, a common mistake is that this base is 2, and this base here is 3, and then that base there obviously is 1. So last thing we could then do, remember the sum of all displacements, S1 plus S2 plus S3, add them all together. A total distance of 16.5 meters. Okay? Alright, we might have to leave it there. My poor little laptop we're struggling along. The cadet people will need to, well, they've got to get the booklets, unfortunately, so they're just going to have to play catch up for the rest of us. All right.